Welcome back. We're continuing our discussion of reinforced concrete design. And in this lesson, we're going to be moving on to the doubly reinforced rectangular sections, or what we call the DRR sections. Now, prior to this, the lessons have focused mainly on singly reinforced rectangular sections, or our SRR problems, in which I had steel located in just one side of a rectangular beam. So for us, in this case, now we're looking at, well, what happens if I have steel that I want to count on for strength in some other location of the beam other than the tension side. So imagine that in the SRR beam, we didn't have this guy for a positive moment, but we did have AS. Now we're looking at saying, well, I'm going to put another lump of steel, a different pattern or whatever, that we're going to call as AS prime, and that's going to be located at some distance that we're going to call D prime down from the top, whereas before it was D that looks something kind of like that. And so depending on what this D prime dimension does, this guy could be compression, he could be tension. It gets a little confusing, but we'll show you how we can handle that and it's not too terribly difficult once you understand the picture. We're going to go back to Whitney, we're going to revise the Whitney blocks a little bit, and then we're going to basically rederive the equations, and we'll walk you through the procedure for how we would start to analyze the doubly reinforced. Okay, now in the DRR section, in addition, sometimes we do put steel into other locations, and particularly within the compression region, and there are several reasons why we would do that. Okay, adding compression steel can greatly help with any sort of changes in stress that occur due to handling or precasting or anything like that, where you might get some cracking in regions other than what we had expected. Right. So for handling and erection purposes of precast, it's not uncommon to come in and put some additional steel. I've got a bit of a glare here. Sorry, I was a little distracted trying to get that squared away. Okay, I think that's a little better. Okay. All right. The second reason is that the dimensions of the beam could potentially, if you have a section that is too small, that compressive resultant from the Whitney block could end up becoming too large for the stress block that we're developing. Okay, because remember, we always said that C-res back in the rectangular case was 0.85 F prime C B times A. Okay, and suppose I could end up with a much larger value than what the concrete itself is capable of carrying if under certain circumstances. All right, maybe it could be some sort of inverted T kind of arrangement or something, and the stresses that show up here, could be greatly overstressed in comparison to just a normal rectangular section. So what we can do is to help out the stresses in the top of this beam, I can put steel in compression up in the top of the beam. Okay, so we'll keep that one in mind as we look forward as well. Compression steel does a great job in helping with cracking. It prevents cracking from opening up. It helps with vibrational behavior. It kind of changes the stiffness of the beam in general. Okay, but the biggest factor probably is the impact that compression steel has on creep and shrinkage. If you remember, creep and shrinkage were long-term deformations or increases in strain that occurred for a wide variety of regions. One of them was, thermally related, evaporation and that kind of thing. And then creep was just under the very nature of a beam with load held on it, that it continues to deflect for time, over time. And so compression steel will help you tremendously in that range and helping it. That's probably the most important reason for including it. Okay. And then, from a detailing standpoint, it also provides some support for stirrups. Now imagine that we have just a simple U-shaped stirrup on here. If I don't have these two bars, this becomes rather hard to place, right? I need something to tie off up here in order just to kind of hold that bar vertically while I pour the concrete in from the top around there. Because if it's just tied off here, this thing can kind of rotate into the plane, when I put the vibrator, and that's not uncommon. So this kind of gives you a tie off point. So a lot of times in beams, we'll run a minimum bar size of a number 3 or a number 4, or even just a wire, just to help with this process. Well, if I'm putting steel there anyway, we can always count on it for some extra strength if we need to. It kind of makes sense. So these last two are probably the most important reasons why we like to have steel in other places other than what's needed for tension. Okay, now the procedure for analyzing this is exactly the same as what we did with the SRR sections, except now the picture is a little bit more complex, but it should make perfect sense. Okay, all right, so what we have is we have our rectangular section. Everything else is still the same, okay, that we're saying that D is from the top of the beam to the bottom. Again, we're assuming a positive moment or tension steel in the bottom. Okay, that's my H. And then I have my B width. So all of that's still the same. And like I showed you before, we're locating this AS prime steel at a distance of D prime down from the top. Okay, so if you recall, the method for analyzing this was the first thing that we draw is our strain diagram. Okay, and so we have our ultimate strain in concrete up here. Again, that's usually 0.003. Okay, and then we can go through and we can start to analyze it. Now, if you'll notice, what happens is at the elevation that we had where the tensile steel was, that was our epsilon S. That's no different than what we had before. This guy still drives the design of the phi factor, okay? Epsilon S or epsilon T, whichever it is that you're looking to use. But now we get an epsilon S that occurs here, and this is the part that makes it a little bit trickier to deal with, okay? That now there's some force associated with the steel at this location, okay? And it will correspond to the strain. So if we look at it, we can go through and we can modify our Whitney block, ever so slightly. Remember that the neutral axis is located at a distance of C from the top, okay? And that means that the tensile steel is a distance of D minus C from the neutral axis, okay? Well, then it stands to reason that the compressive steel, I can say, is C minus D prime, okay? And so we've got all of our dimensions. Once we figure out C, I know the strains and I can find everything else. So it's just a matter of doing proportions and checking whether or not things have yielded, just like what we did before. Okay, so Whitney then says that I'm going to take this C and turn it into an equivalent stress of 0.85 F prime C over some area of A, and we know that A is equal to beta 1 times C. Okay, and beta 1 was a concrete property, just like what we did before. If you're struggling with this or you don't remember, go back and look at the SRR videos where we set this up, and that will explain it in further detail. Okay, all right, so then once I have my stresses figured out, we can figure out, well, the concrete stress, remember this 0.85 F prime C is stress in the concrete, all right? And so that's how we calculated C res, and that was always located at a distance here of A over 2 for the rectangular section, okay? But what we pick up that's different, well, we do get the tension steel, that's still the same, ASFS, and usually we want that to be ASFY, but we'll verify that. Okay, but the one that we pick up extra is now at the location of the steel here, I pick up a force in those bars in compression. Okay, and you'll notice that, because it's in the negative region of the strain, this guy's going to have a negative stress, which means he's going to be a negative force, which means he's going to be in the same direction as this guy. Okay, and so that will be an important factor for us as we look at that. So that's kind of how we set up the Whitney block. It's not really difficult. Okay, it's very similar to what we did before, except now we have a CS that shows up for the compression steel. Piece of cake. All right, so now, just like before, we'll go through these next calculations fairly quick, okay, because it's exactly the same process. So now we're doing sum of forces in the X. And again, I'm doing this direction positive. And so this is TS minus CS minus CC equals 0. Okay, and then all the pieces that we know, TS is now going to be AS times FS. And again, we're hoping that that's ASFY. Okay, and then CS is AS prime times FS prime. Okay, so just like what we did with the tensile steel, now we're doing it from the compression side. Now we're going to ignore buckling and other things that can happen on compression because hopefully the concrete is binding that steel enough that it's truly just an axial behavior. Okay, and then my C sub C is still 0.85 F prime CBA. Okay, again, FS is the stress in the tensile steel, FS prime is the stress in the compressive steel. Okay, so then I can go in and I can sum moments, and I'm going to sum moments about the top point, again, because all my dimensions were measured from there. So if we look at our section, we're going to sum moments on this diagram. We're going to sum here, right? Because I know from here to here is D prime, from here to here is A over 2, and from here to here is D. All right, so if I do that, the moment equation looks exactly like the following. It's going to be my tensile steel side, so this is my T, S, okay, times D minus CS times D prime minus C res times A over 2. That will get me my nominal moment capacity. Okay, now there are some issues that happen here. Hopefully we're designing this so that FS has yielded. Well, the two cases that can happen on this are, the first case is that both the tensile and the compressive steel have yielded. which basically means that Fs is equal to Fy and Fs prime is equal to Fy. Okay, but the only way that this happens is by looking at the strains. And so we're looking at the strain in the tensile steel greater than the strain in the yield strain, and that the strain in the compressive steel is greater than the strain in the yield. So you can tell right now we're going to make an assumption, and then I've got to verify the case. Okay, so superposition, says that if that's the case, what I can do is I can kind of break this into two separate pieces. Okay, for analysis. The first one involves just what the steel is contributing to the overall moment capacity. Okay, and so we're going to split that T-res and say that that's equal to TA plus TB. And I think I wrote it as T1 and T2. Okay, that we're going to attribute a portion of the steel in tension to being what balances the compressive steel. Okay, and you can see that's what I did. So I say that T1 is the same area of steel multiplied by Fy. And what that does is that produces a moment and it sums those forces and knocks those out. And then I can come back, and because I've already counted for that portion of steel, T1, that then I can come in and say, well, the rest of it goes over here, that's just ASFY minus what I accounted for over here. And so these two diagrams together give me the Whitney block that we had right here. Okay, so we take this picture and we split it out a little bit to be able to analyze it. Okay. All right, so what we do then is we can come in and say that I can calculate the moment on this region as just simply being AS prime times Fy, again, assuming that Fs prime is Fy, okay, multiplied by d minus d prime. So you'll have all of this stuff in an analysis problem, okay? And again, we made an assumption here, but we'll have to verify it with our strains here at the end. Okay, so that gets us our diagram for A. For B, we do the same thing with that one, okay? And so we compute the moment diagram like we did before. And so now it's going to be, instead of ASFY, it's now that T2 value. Okay, so we're going to do ASFY minus AS prime Fy, then multiplied by everything else. Okay, that's T2 happening there. Okay, and so that's AS, and that's what we're showing, and then the rest of it is D minus A over 2 is our moment. So this is kind of the similar formula to what we did with the rectangular section. Okay, and in this, only A is unknown in this, okay? So what we do is we sum forces in the x direction on this picture, and you get AS minus AS prime times Fy is equal to 0.85 F prime CBA. Okay, and I call this as T-res. This is actually T2 minus C-res. Okay, it was T-res when we did the singly reinforced, but this T2 is the second diagram over in B. And so I can solve for A. Okay, now with A known from that equation, I can then throw it back up into the moment equation, and I can calculate that nominal moment Mn2. So this is the step that we're looking to do. Okay, and that will get me my nominal moment for it, if everything yields. Okay. Now, the only thing that remains for us then is that we do have to check our assumptions, because we don't know the state of Fs or Fs prime. Okay, and so we assumed this, that these were my assumptions. So we have to verify then that each of those assumptions is correct. And the way we do that is by looking at the strains. We calculate the yield strain and compare it to epsilon s, and we calculate the compressive or the yield strain and we compare that to epsilon s prime. Okay, I have to meet both in order to meet both of these requirements, because I assumed both of those. Okay, and from the strain diagram, we can then use our proportions, and use that A value to get our C, and then use our C to get our strains. So you'll recognize this one. That's the exact same formula we did before when checking epsilon s. Okay, but now I've got a different proportion that I can do, in which I have epsilon s prime is to C minus D prime is the same as epsilon Cu to C, right? And that's where I get epsilon s prime. So when you calculate epsilon s and epsilon s prime, if they're both greater than the yield strain, then I'm good. This was the right method. Okay. Unfortunately, there's no way to know until I get to this point. All right. Okay. And so that's what we're looking at. Okay. So if epsilon s prime is greater than epsilon y and epsilon s prime is greater than epsilon y, we can determine our phi factor, and then we can compute our phi mn. Okay. But what happens if this isn't the case? Say we violate it, and there are a couple of cases that we'll look at here as well. Okay, you know, the methodology still works, but what happens if epsilon s is less than epsilon y? Okay, well, the possible solutions for us to be able to do this are as follows. Okay, I can reduce the area of steel in tension, okay, which that will reduce my rho, which will always increase my epsilon s. All right, I have less area means it's got higher stress, means it's got higher strain, okay, but sometimes that's not always possible. Okay, maybe, you know, for moment capacity reasons, you know, I needed that extra steel. Okay, another possibility is that if possible, can we move the tensile steel further down in the cross section? So say my AS was up here, and I was getting an epsilon s that wasn't sufficient. Okay, can I move the steel down to another location in such a case where the final is acceptable? Okay, again, this steel works best in this strain diagram when it's as close to the tensile fiber as you can get. It's more efficient, it does more work. But sometimes I can cheat this, you know, a half an inch or an inch, you know, if I'm very, very close to my capacities. Now, again, you've got to maintain your cover requirements. You've got to be, you know, keep your eye on all of those details. But everything else works, you know. So what happens when I do that, when I move this down, the variable that's changing, remember, that was D. You've changed D. Okay, A is still the same, especially once I get it to yield. Okay, so, but by increasing D, I increase D minus A over 2, which in turn is going to increase epsilon s. Okay, this also has the added benefit of allowing you to also reduce AS, okay, while maintaining the same moment. Okay, and if I reduce AS, then I reduce the area of steel in this section, and if I reduce the area of steel, that increases the stress, and if I increase the stress, that increases the strain. So you're getting a 2-for-1 by relocating the steel to a more optimum location. Okay, so all of this is compounding to help increase reducing rho, but while maintaining my MN value. Okay, the other issue that we have, and this was one of the ones I guess I didn't have it on the list before, that if we have a case where, again, we're examining the case where epsilon s is less than epsilon y on this, is that by adding additional steel and compression, I can actually force this guy to yield, okay, or increase the strain in my tensile steel. Okay, and so by adding additional steel to AS prime from the Whitney stress block, we can rearrange this so that if we increase CS, which is this was coming out of that B diagram that we had, then TS must increase in response in order to balance this. You know, again, we're looking at, get my page here. Oops, wrong page. Somewhere. Got my pages out of order here. I'll try this again. Again, we're playing on diagram B, right? So if I decrease, you know, if I add to this value, okay, then I'm going to increase the strain to correspond to the corresponding C-res value, and that's all that we're looking at here. Okay. Okay, so if TS increases, the stresses will increase, which will increase epsilon s, okay, by Hooke's law, because again, sigma is equal to E times epsilon, so sigma in steel is equal to epsilon s in steel. So that's kind of a pretty useful little step for us. Okay, so that's how I can get epsilon s to yield. All right. Okay. Now, and that's a requirement for ductile failure. Okay, so we've now made it yield. Now we can go back and we can kind of look at, you know, what we need to do with epsilon s prime. Okay, and there's some issues there. Okay, so for both of these cases that we're looking at, the case 1 that we just did and this next case, case 2, the tensile steel has to yield. Okay, so that gets us to here. So now we're coming in, okay, maybe we have the situation where the compressive steel has not. So now we're at epsilon s greater than epsilon y, but epsilon s prime is less than epsilon y. This violates our assumption because this one tells me that fs prime is not equal to fy. Okay, and that was one of our assumptions. Okay, so what we do is, you know, if this is the scenario, what we can do is we come back in and we go back to our Whitney block. So again, this is sum of forces in x equal to 0. This is positive. Okay, and so this is that same formula that we had, tensile steel minus compressive steel minus concrete compressive resultant. Okay, but what changes is, so we've yielded it, so I now know that that's true. ASFY is my tensile value, but this is the one that we've got to kind of look at now. Okay, because I have to figure out, I have to compute FS prime. Now recognize that Fs prime we said was E times epsilon S prime. Okay, so once I find the strain, I can calculate the stress. So all we have to do then is, where before we had A was ASFY minus AS prime FY, okay, the only thing that's changed is this guy right here, is that Fs prime value. Okay, and so depending on whatever his value is, that will set my A. Right, so we'll calculate our A, and then we'll come back around and start to check. So using strain compatibility and Hooke's law, we can calculate based on its position in the section what epsilon S prime is. I showed you that. This is that relationship for the proportions, and I multiply that by E for steel. I can get you our epsilon S prime, okay? And so then the stress of this is all Fs prime. So once you know the strain, I can get the stress. Okay, and so then it's just a matter of plugging in all of the parts that we have happening here. And what I like to do, so this was what came out of the strain proportions with the C's and the D prime. You can actually rewrite this a little bit as A minus beta 1 D prime all over A. And so since I've got A from this calculation and D prime I know and beta 1 I will know, then I can check this. Okay, and so what we want to make sure is that the Fs prime that we're solving for, you know, using the true value. Now, if it's less than Fy, I use Fs prime in the formula. If you do this calculation and you find out all of a sudden that Fs prime is greater than Fy, then you've got to go back and you have to limit this, you know, that our Fs prime maximum value can only go to Fy. You can't, you know, if there's 60 KSI steel, I can't put 80 KSI into the compressive steel. Okay, and so that's how we start to kind of analyze all of this. So this becomes my formula for Fs prime. Okay, with the only unknown being the A that you're calculating. So you kind of iterate through and you can quickly start to solve for this. All right, so all we're gonna do is do a little bit of algebra and kind of derive out our formulas, right? So here's our equation, ASFY minus AS prime multiplied by that strain relationship minus our compressive values, 0.85 F prime CBA. So again, this was TS, this was CS minus, and this was minus our C res, and all of that's equal to 0. Okay, so all I'm going to do is do a little bit of algebra. It gets a little funky, but it's not bad. Okay, and when I do that, all of this is equal to 0. And what you notice in this equation, when I simplify it, I'm going to collect all the terms together, and you'll notice that I have an A squared term here, I have an A term here, and then a constant portion here. This sucker is quadratic in A. Okay, and so now with that, I can use the quadratic formula, you know, which we know is some form of A times x squared plus bx plus c equals 0. The quadratic formula then, in our case, x is our little a, can be given by this. Okay, and so what I can do is I can actually do a quadratic expression and solve for the a that satisfies that equation. So my a then is 0.85 f prime cb, so this is kind of c res divided by a. I've got my b, which is the strain in concrete times the strain in the Young's modulus of steel times as prime, and then minus asfy. Gets me my B value, and then C is this quantity here. Okay, and so you can use your favorite solver, Excel, your calculator, or whatever the case may be. Okay, to pick off all of this gets me to A being equal to some numeric value. Okay, once I have that, then I can go in and I can calculate Fs prime. And once I have Fs prime, then I start doing our checks. Okay, if Fs prime is greater than Fy, we recompute the moment Mn using the case 1 methodology. Okay, otherwise this case is correct, and then we can proceed on to our approach. Okay, so finally, once you've gotten all that down and you've got your A locked in and you've figured out which case that you are, the general nominal moment capacity equation for a doubly reinforced beam looks something like the following. It's ASFY times D minus AS Fs prime times D prime minus 0.85 F prime C BA and then A over 2. Okay, and that will get us our case for there. Okay, and then finally, once you've got all of this, you do need to compute the tensile strain and the epsilon T value in order to be able to get your phi factor, but you do that anyway whenever we go through. But that's our basic approach. So anyway, I hope that makes sense. And with that, we'll show you kind of the walkthrough that we typically do. Okay, so maybe you have a problem that looks something kind of like the following. Okay, I have a rectangular section. It has a width of 11 inches, a D of 20 inches. I'm not too worried about the H or the cover on this. And in this, I'm putting 6 number 9s in the bottom, and I'm putting 2 number 10s in the top, and I have a number 3 stirrup on this. Okay, so and then we have a positive moment applied to the section in term that's the M. Now, again, I'm not worried about what the load is or what this is. We're actually wanting to find what's the nominal moment capacity or the design moment capacity of this. So the first thing I would do is I figure out the variables that I need. I need my AS, so that would be my 6 number 9s. Write the area. AS prime is my 2 number 10s. Write the area. We come up with our H. This is where we're going to use that rule of thumb. This is 2 layers. So you would do D plus 3.5 inches. We'll get you a first guess on H on those. Okay, and then we can compute we've got our D is 20 inches and our D prime is 2.5. Now again, I called out D, but I didn't call out D prime here. This was kind of an exercise to make sure that you recognize that that's what that dimension was. Let's just start set up. Okay, so once you do that, then all you do is you draw your Whitney stress block, and then I make sure that you locate CA, epsilon S prime, and epsilon CU. So this is just a reproduction of the picture. And like I say, in my classes when I do this, I try to encourage the students not to look back at the notes, to try to reason through where the parts are. That will help burn it into your brain. But you notice it's the same approach that we did with the SRR beams. I'm doing a rectangular section, strain diagram, Whitney stress. And so that's no major issues there. Okay, once you do that, once you get the Whitney stress, then what we do is we sketch the resultant forces. So you would have a C-res and a CS and your tensile. Okay, and then clearly identify their location. Remember that C-res is at A/2 from the top. Our CS is located at D prime, and then our TS is located at D, all from the top. Okay, once we do that, basically we take that picture and we basically run through the process. We write the force equilibrium equation for Whitney stress block. Okay, I locate the net neutral axis, which means I either find A or I turn around and find C. One of those two will get it for me. Okay, because again, if I get A, I know that beta 1C, that it's that guy, so however you choose to go to it. Okay, and then you come in and you have to find epsilon S and you have to find epsilon S prime for the strains in the steel. And then with those, then we can come in and determine the stress in the steel. So again, you've got to find FS and you have to find FS prime. But remember that those have to be less than or equal to Fy. Okay, you can't exceed Fy. Okay, if you end up over that value, then that dictates which of the methods that you were going into. Okay, so we're going to be capped as our maximum limit here on these guys. Okay, so once I have the stresses figured out, then I can go in and I can calculate the nominal moment contribution from the AS prime. Okay, so this is my A case from our scenario, and then we can compute the nominal moment contribution from the concrete resultant. That was the B scenario. And then finally, you can compute the total nominal moment here, that this guy is just going to be MA plus MB as the two portions based on how we broke that picture up. Okay, and then from that, then I can take phi MN is equal to whatever. Okay, once you find your phi value, you're good to go. So anyway, that's kind of the approach for a doubly reinforced rectangular section and the analysis process that's required for both. So I hope this has been pretty clear to you. As always, if you'll leave us some comments, let us know how the video worked for you, or if it didn't, and what we could do to make it better. Please let us know. We're always looking at that feedback. And as always, toss us a like if you like the video, and please be sure to subscribe to the channel. Hope you guys have a great and wonderful afternoon. Thanks. Bye.